Hello students, in today's lecture video we are continuing our chapter 9. Okay, so we are learning about conjugate acid-base pair, how to recognize the acid-base pair, and how to know the relative strength of acid, how to recognize them. Okay, so let's start today's class. We already know that acids are those compounds who are capable of giving away the H plus. And bases are those compounds who accept that H plus. Okay, bases may have a lone pair of electrons in them. That's why they are rich in electron, so that they can make the bond with electron poor H plus. Okay, that gives you idea that acids and bases, they can react with each other. They can make the relationship with each other, right? So let's see that reaction of acids with base with an example here. So I'm bringing here, right? I'm bringing here HA, representative acid. Okay, any acid I can represent that as HA. It's a general representation. And I can have a base B. Generally the base, if it is neutral, then it has a lone pair of electron with itself. Okay, then this acid can lose the H plus, right? That H plus, after it loses, whatever is left over is A minus. So that A minus is one of the product, right? We call this conjugate base. So the acid which after losing the H plus, whatever is left over, that leftover species is known as conjugate base. Okay, and now let's see base. We have base B. After gaining that H plus that was given away by acid, now it becomes HB with plus charge on it, right? The product is known as conjugate acid. So I can read this. Every acid can form a conjugate base as a product with a reaction with base, and base can form a conjugate acid as a product, right? So every acid-base reaction have a pair, right? They do have pair on the opposite side of the arrow. So acid will have a conjugate base on the opposite side of the arrow. Base will have the conjugate acid on the other side of the arrow. So this acid with conjugate base is known as conjugate acid-base pair. The base with the conjugate acid is also known as another conjugate acid-base pair. So total we have two pairs here, right? Two acid-base conjugate pairs. So the product and whatever written here is something that I just mentioned. Let's see this with a real example. Now I bring in hydrobromic acid, HBr, and I react that with water. Okay, so this is acid, means I can give away that H plus. So when I lose that H plus from HBr, I will have leftover of Br minus. This is a conjugate base. Water is a base. After gaining that H plus from the acid, it will form conjugate acid. It will form hydronium ion. So acid has the conjugate base on the other side of the arrow, right? And base has the conjugate acid on the other side. Okay, you can read that one here. So HBr and Br minus are the conjugate acid-base pair. Similarly, the water and hydronium are another conjugate acid-base pair. And in any acid-base reaction, there are always two conjugate acid-base pairs. Okay, now let's try to recognize the conjugate acid-base. Okay. Name of HF. First of all, HF. What is this? It is an acid. It has a hydrogen in the formula, right? It is an acid. What is the name? HF will form FH plus and F minus. F minus is fluoride ion, right? If it is ide ion, if you remember in earlier lecture video, if we have the ide as an ion, it becomes ic acid, and we also need to add hydro. So it becomes hydrofluoric acid. Okay, so HF is hydrofluoric acid. Write the acid-base reaction of HF in water. So let's bring HF plus water. Let's write it. Right, so we will have equilibrium reaction over here. So, and now we have here HF will break down as H plus and F minus. That H plus will be given away to water, so whatever left is F minus. After gaining that H plus, water will become hydronium ion, right? So this is the full reaction here. Now identify acid-base conjugates. Okay, so this is acid, HF is the acid, water is a base, right? And I have here the leftover, or I can say the conjugate base, right? The acid gives away the conjugate base, forms the conjugate base, and base forms the conjugate acid. So I have here conjugate acid. Okay, so both conjugates on the one side of the arrow, both acids base on the other side of the arrow, just to make sure that you are doing it all right. Okay, so that is how we do it. Can you try this? Name NH3. Oh, NH3 is a weak base. It is a base, right? Because we know the nitrogen has the lone pair, right? This is not, the H is not the protic acidic proton. NH3 is always a base. Now write the acid-base reaction. So base, write the reaction of ammonia in water. So I bring the water. Now since ammonia is a base, then water will act as an acid. Okay, so we will write here. Now since water is an acid, it is the water who gives away the proton, because by definition acids will give away the proton. They are the proton donor. They are the hydrogen ion donor, right? So water, after giving away that proton, there is left OH minus, right? H is given, left is OH minus. So this is now conjugate. Can you guess what is it? Acid will form conjugate base. So this is conjugate base. Now let's go back. The base ammonia takes in that H plus, right? And that forms NH4 plus. Okay, so we have here NH4 plus, and actually I should have written that as NH4 plus this way, right? So we have here ammonium ion. The name of this guy is ammonium ion, and this is formed from the base, so it is a conjugate acid. Okay, so the question says us identify acid-base conjugates, so we just did that. And NH4 plus ammonium is the conjugate acid, OH minus is the conjugate base, ammonia is a base, water is an acid here. Okay, so conjugates on the other side of the arrow. Now let's do the learning check. Write the conjugate as base of the following. So it means that these guys are acids, right? And you now need to write the conjugate base, right? Think about it. Acid means they are proton donor, right? So it means they would like to give away those protons, and whatever left, that is the conjugate base. So when HBr lose away that H plus, left is Br minus. So Br minus is the conjugate base here. right? H2S. Yeah, this one is H2S. When one of the H plus is given away, the leftover is HS minus. This is the conjugate base of H2S. Similarly, you can try here carbonic acid. We have H2CO3. This is an acid. You need to give away one H plus, right? When H plus is given away, then leftover is HCO3 minus. So that is the conjugate base here. Okay, how? Because H2CO3 means it has two H pluses and then one carbonate ion, right? One of the H plus is given away, means there is only one left. So H plus and CO3, 2 minus, makes us H3OC minus. Okay, the charges are taken here, one of the plus, two of the minus, so leftover is one minus. So we call this HCO3 a bicarbonate ion, something that you might have learned during naming the polyatomic ion, or we call it hydrogen carbonate if you go for the name of this. So this is hydrogen carbonate or bicarbonate. This guy is the conjugate base here. Okay, is that clear? If it is not clear, please pause the video, work by yourself. All these given HBr, H2S and H2CO3 are acid. Then work from the definition of acid. If they are acid, what is their nature? Their nature is to give away the H plus. So take away the H plus. Write down what is left. Okay, if you are good with that, let's move on. Write the conjugate acid of the following. So it says write the conjugate acid, means it is telling you that these guys are bases. Okay, these guys are bases, means they do have a nature of accepting the proton, right? Because bases will accept the proton. It means add the proton to them, whatever is formed is the conjugate acid. So if you add H plus to the NO2 minus, it becomes HNO2. So this is the conjugate acid, the corresponding acid, right? If you add H plus to ammonia, we just did that in earlier slide, it becomes NH4 plus. So it is a conjugate base here. Sorry, the base gives conjugate acid. I should write here. The base gives conjugate acid, right? Now, OH minus is the base. It means it can take in the H plus. So when you add H plus to the OH minus, then the charge is here is 1 plus 1 minus, and we have water that forms. So water is the conjugate acid of base OH minus. Okay, I think that makes it clear. The bases make conjugate acid, acids make conjugate base. Right? That's how the pair works here. Now you can try a few more examples here. The conjugate base of this acid, right? Conjugate base of HCO3 is, what is it? It means this guy is an acid here and you need to find the conjugate base. If this guy is acid, means that H plus can be given away. When you take the H plus away, it forms, the leftover is carbonate ion. So carbonate ion is the conjugate base, right? Let's try the second one. The conjugate acid of HCO3 minus. Now we have the same species, bicarbonate ion. Now conjugate acid is asked, means right now this is acting as a base. Okay, that's why it is important to see what is that species first, whether it is acid or it is base. And from there, you know use the nature. What is their nature, right? That's how to proceed this kind of question. Okay, so we have to find the conjugate acid. This is a base. Base means it will accept the H plus. So add one more H plus here. When you add H plus to this, it becomes H2CO3, right? So H2CO3, this is a carbonic acid. This is the conjugate acid of that base. Let's try one more. It's fun. Conjugate base of water. So it means right now this is an acid. Make a conjugate base. Acid means take away the H plus. If you take away the H plus from here, the leftover is OH minus. So OH minus is the conjugate base. If the question asks you, write the conjugate acid of water, means right now the water, sorry, I wrote water. Water is a base, right? Water is acting as a base. So add H plus to it. Okay, when you add H plus, it becomes hydronium ion. So hydronium ion is the conjugate acid of the water. Okay, do not jump into the answer. Do not jump into the choice because the choices are always confusing here. You have to understand the concept, apply that concept, and I just showed you how to apply the concept, right? Step by step. That will make sure that every time you are choosing the right answer. And the answers are here. Now, let's talk about amphoteric compound. Okay, something weird you saw in the earlier slide, right? Let me show you here. I have HCO3. Sometimes it was acting as an acid. Sometimes it was acting as a base. I had water. Sometimes it act as an acid. Sometimes it act as a base, right? Because these guys are special. They are amphoteric compound. So amphoteric compound means a compound that contains both hydrogen atom as well as lone pair of electron. It means it can be either acid or it can act as base, depending on who is the one that you are fighting with or neutralizing with. Okay, if the base comes to interact, water becomes acid. If an acid comes to interact, water becomes a base. Okay, so that dual nature, right? The amphoteric compound have the dual nature because they do have the hydrogen atom, sorry, as well as they do have the lone pair of electrons. Okay, so let's see here. When you write the water as a base, then you are talking about the lone pair of electrons on the oxygen. Now, when H plus comes, you make the bond with the lone pair of electron, right? Electron rich area, bonds with electron poor proton forms conjugate acid here, right? Hydronium ion. Whenever water act as acid, means now that one of the hydrogen can be given away because oxygen is more electronegative in nature. It will pull that shared pair electron towards itself. That makes the hydrogen acidic, right? So now that hydrogen poor in electron can be easily removed. Whatever left is conjugate base, right? After losing H plus, I have OH minus here. So water can act as a base as well as it can act as an acid. It just depends on who is coming to interact it with. Okay, another example we saw was bicarbonate ion in the earlier slide. The bicarbonate ion is also an amphoteric compound. Now, with this slide, we are going to talk about the strength of acids and bases. Okay, we will talk about the relative strength when we compare two different acids or when we compare two different bases. So whenever we talk about strength, means we are talking about who is more stronger. Okay, so we can have a classification of acids as strong acid and weak acid. We can have strong base and weak base. Okay, so who do we call strong or who do we call weak? Let's see here. When acid dissolve in water and 100% of it will dissociate into ion, then we classify them as strong acid. So strong acid will dissociate 100%, means all of the H pluses will be given away, right? All of the H pluses will be broken down into H plus and Cl minus in this example, and then you will have 100% of dissociation. That makes the HCl a strong acid. Whenever we write the reaction of strong acids, we just write a straight single reaction arrow, because it means it is undergoing, the products are predominant, the reaction goes to the right hand side, all of the reactant will form the product ultimately, right? The product is greatly favored at equilibrium. That's why we have a single arrow here. Okay, some common strong acids are hydrobromic acid, hydrochloric acid, hydroiodic acid, hydrochloric acid, sulfuric acid, nitric acid, perchloric acid, chloric acid, etc. Let me write here few more that are important to you. Perchloric acid and chloric acid. Okay, how to write the formula? See earlier lecture video. We have a slide there for the formula of these acids. So altogether, there are 7 acids that are strong acids that you want to memorize it. Okay, because right away you want to know them. These are strong acid. So HCl, HBr, HI, sulfuric acid, nitric acid, perchloric and chloric acid. These are the strong acids. Okay, generally any other acids outside of this club of 7 acids, they are weak acid. Okay, that is just my quick way of looking at. Okay, and I'm giving that information to you. Okay, so when we have an acid that dissolves in water, but only a small fraction of acid dissociate into ion, then we have a weak acid. In those cases, we have somewhat unequal reaction, right? The forward reaction is less favored. The reverse reaction is more favored. So we write our equilibrium reaction there. Okay, we write either double arrow, or they just mention one is longer than other arrow. Okay, so, or you can understand, they go into equilibrium. It is not a one-way highway. It's two-way lane there. Okay, because the reactants are favored at equilibrium. So we have here a reversible reaction, right? Reaction that goes into equilibrium. Example is acetic acid. Okay, so those acids who will give away the proton, but they are not very readily giving away. They are not giving it right away, or they are not giving all of what they have. They will not dissociate into 100%. Only some of the ions will be there, right? And those ions will, the product ions will combine together and put and make the reactants back. That's why you have lesser fraction, lesser percentage of the ions in the solution. So we call it weak acid. Okay, if you remember electrolytes, right? Long time back, we might have talked about electrolytes. So the strong acids are strong electrolyte, weak acid are weak electrolyte, because they are forming less number of ions in the solution. They have more of the reactant molecules. Okay, so that is the weak acid definition. Some of the common weak acids are phosphoric acid. The one that I would like student to remember is this HF, hydrofluoric acid, is a weak acid. All other in the same column like HBr, HCl, HI, these guys are strong acid, but their friend HF on the same column of the periodic table, this guy is weak acid. Okay, remember this, because many like student make error here. They think HF is also a strong acid, which is wrong. HF is a weak acid. Okay, and if you ask why, it has to do something with the size of the fluoride ion. The size is too small that it okay, that makes it weak acid. Okay, it does not want to give away the H plus that is given away, because the bond between the H and F is very strong. If it is very small, right, and H plus is also small, the two small things are having very strong bond between them, and it is hard to broken down. Anyway, so that is just if you ask why. Otherwise, you are fine. Another example is carbonic acid, HCN, hydrocyanic acid. These are weak acids. Okay, so 7 acids are the strong acids that we talked in earlier slide. Rest of others, any other organic compounds that has H in their formula, all the organic acids are weak acids. Okay, so yeah, just what I mentioned. This is a slide with a picture. A strong acid, HCl example, completely dissociates. Weak acid, mostly undissociated acid, means there are few ions, more of them are the molecules present. Okay, and if you want to remember the strong acids, some examples are HBr, HI, sulfuric, nitric, perchloric, and the chloric is the HClO4, right? So we have here all these strong acids. Now, let's talk about their strength. This is about bases. Okay, now strong base and weak base. Similarly, the definition works for here. 100% of base dissociates means that we have a strong acid. Examples are sodium hydroxide, potassium hydroxide. When you put them in water, all of them will make the ions, right? They will dissociate 100%. If we have a weak base and we dissolve that weak base in water, now if only a fraction of the base dissociate, then we have a weak base. Example is ammonia. Okay, ammonia will form some of the ammonium ion and hydroxide ion. Now these two ions will combine and can form the reactants back. It is an equilibrium reaction, okay, the reversible reaction, and the reactant is more favorable. That's why we have small fractions of ions here. Okay, so that is the case of weak base. We can, so to understand the reaction, the stronger the acid. Now let's talk about the conjugate base. Whenever we have a strong acid, then the corresponding conjugate base is always the weak one. Okay, so this red color coded word here is important to understand. Stronger the acid is, weaker will be its conjugate base. Okay, this will be helpful whenever we are comparing two acids and then we compare their conjugate base. Always the stronger acid will have the weaker conjugate base, or we can say the weaker acid will have the conjugate base that is more stronger in comparison. Okay, so strong acid will have weaker conjugate base here. Okay, the reason, if you want to know why this happened, is the strong acid means it is giving away the H plus, all of the H plus and Cl minus, right? These are the products. Now this Cl minus does not want to react with H plus and give away the HCl. This does not want it. So the forward reaction is more dominant. The reverse is not, right? That's why we have a weak conjugate base there. So relative acid strength is a useful tool to predict the direction of acid-base equilibrium reaction. Okay, and generally we use this chart. If any question comes related with the strength, then this chart should be available to you so that you can explain it. Stronger the acid is, weaker will be its conjugate base. So here this chart shows you the acids in the category. We have here weak acids down here and strong acids. The acid strength increases as we go up. and corresponding conjugate base are shown, their strength will increase as we'll go down. Because stronger the acid is, weaker will be its conjugate base. Okay, so let's say if we just compare the HI and HBr, according to this chart, HI is the strong acid, right? Because the strength is going up. And comparatively, HBr is a weaker one, right? Weaker than the HI. Then here, the iodide ion will be the weaker conjugate base. Okay, the weak acid, the relatively weak HBr will give you relatively stronger conjugate base. Okay, so that is what we have to understand. Stronger the acid is, weaker will be its corresponding conjugate base. That is how we talk about the relative strength of acids and their conjugate base. Okay, so in today's lecture video, we learn how to recognize the conjugate acid-base pair. We learn how to write the conjugate acid if the base is given and vice versa, right? We learn about amphoteric compound and we learn about the strengths and the fact that stronger the acid is, weaker will be its conjugate base. And this is a helpful tool whenever we are looking at the equilibrium reactions. Okay, so that is what we learned, and we will continue the rest part of the chapter in next video. Keep on watching, keep going studying and working on your homework, Connect homework, as well as the quizzes and other worksheets. See you in the next lecture video. Thank you.